So now I will present our work on integrating graph and transformer-based models for enhanced chemical disease relation extraction in document level context. So now let's begin. Our presentation today will follow this structure. The first is introduction, the second is method, and the next is experimental results, and the finally is conclusion. Extracting chemical-induced disease relationships at document level is challenging because disparate entity mentions and contact dependencies. As shown in the diagram, entities and relationships span across multiple sentences, requiring both local and global context understanding. Traditional models struggle with these complexities, motivating us to propose a hybrid approach. Our contributions address these challenges. With the first, we introduce a hybrid model that combines transformer-based method for capturing local semantics and graph neural networks for global context. And we also enhance GCN II model to learn more efficient node embeddings. These contributions enable us to effectively extract CID relationships with improved accuracy. So our proposed model consists of three main modules. The first is encoder. Initialize with a pre-trained birth model to learn contextual word embeddings. The next is graph convolutional network. This is to encode structured information about relationships. And the next is classification hit. Apples the predicted relations based on Boolean features, and this combination enables the model to handle both sentence level and document level context. So now I will talk more about the detail. The first is in entity marker. Entity marker is crucial for effective document modeling. We insert special token boundary markers to delineate entities and sentences. This ensures the model can clearly realize key components in the document. And so now is encoder. We use a transformer-based model as an encoder to learn word representations. This study utilized a family of word models. After going through the encoder, we have embedding of each word. And then from word embedding, we extract mention, sentence, and entity embedding to construct a graph. The graph includes different types of nodes and edges in which nodes present mention, sentence, and entities. Edges define relationships such as mention to mention or sentence to sentence link. And the core idea behind GCN is to aggregate information from a node's neighbors. Each node updates its representation by combining its own features with the feature of its neighbors. Let's look at the diagram on the slide. You can see a graph where each node passes messages to its neighbors. After several layers of aggregation, the final output represents learned embedding for each node. However, the original GCN suffered from oversmoothing. Oversmoothing in GCN occur when node embeddings in a GCN become so similar that these embeddings lose unique information, so they become indistinguishable when the number of layers of the network increase. And cause of oversmoothing, the main reason is the repeated aggregation of neighboring node features across layers, leading to excessive information mixing. And GCNII introduced two main innovations to overcome the limitation of the traditional GCNs. And the third is initial restore condition. GCNII combines the info feature with learn feature at every layer. This adds to the richness of initial features and identity mapping with feature transformation. By adding an identity metric to the weight metric, identity mapping ensures that a deep GCNI model achieves at least the same performance like its shallow version. And to make GCNI learn to choose important feature from the initial hidden state and the last state hidden state, we propose an adaptive gated architecture that ultimately controls how information flows through layers. Instead of relying on static coefficients, we use a tunable function, which dynamically balances the contribution of initial and progressive features. And now we also compute local context embedding for each pair of entity to enhance entity pair representations. We multiply attention metric of two entities to get local context attention, and then multiply it with hidden state to get local context embedding. And this diagram shows the way to compute local context embedding for entity ES and EO. And the last is classification hit. For each entity pair, we compute two entity-specific representations by combining entity embedding and local context embedding, and the probability that the entity pair ES and EO has relation R is computed as the above formula. So now in experimental results, we evaluate our model on the CDR datasets. Our enhanced GCNII combined with transformer encoder like BioBot and Cybot significantly outperform previous models. For instance, BioBot above combined with enhanced GCNII achieved an F1 score of 70 of 3.06 compared to the previous best of 71.95. And these results highlight the robustness of our approach for document level relation extraction. And we also experiment to demonstrate the effectiveness of enhanced GCNII, and it can be seen that compared with GCNII, our enhanced GCNII improved significantly. And in conclusion, we propose a hybrid architecture that effectively combines transformers and graph-based methods. We also enhance GCNII solve over smoothing while maintaining discriminative learning in deep layers. And our model open doors to new possibility in relation extraction tasks.